Okie dokie. Let's go back here. All right, so I asked at the end of our last break what was, or before we took our break, which is faster, SCSI or IDE? So we have an opinion, probably a guess, but they were both used. We decided that SCSI was used for server, and IDE is used for consumer. Okay, so let's pose a follow-up question. What does fast mean? What does that actually mean? Fast. Because
it's very opinionated.
Well, when we
he's not wrong.
when we come back here, when we said SCSI, we said this is used for servers. When we said IDE, we said this was used for personal computers. Okay.
So the server, obviously, you'd expect it to be faster.
But still, it comes down to what's fast mean. So server, multiple users at the same time. PC, single user. So we have to think about what is the, how does a hard drive actually work when you are having multiple users requesting stuff from the hard drive at the same time? And this comes down to, kind of hard drive mechanics. So how does a hard drive function? Based on what you guys know, what does a hard drive do? Okay. Okay. And how many things can it read or write at a time? One. Okay, so if you have one user asking for data at once, then that hard drive can keep up pretty well, right? If you have 3 users all requesting data, they're fighting with each other, right? Potentially, because who is talking to the hard drive? So let's go back to this picture. So we have 3 users sitting here who are talking, who are ultimately trying to read something from the hard drive, but 3 different somethings. All right, so 3 different files from the hard drive. Are those users directly interacting with the hard drive? Who are they directly interacting with? Operating system. So they're interacting with a piece of software. So if the user interacts with a piece of software, and this piece of software's job is to interact with the CPU and these other components in the smartest way possible, whatever that means. The most optimal way possible. Again, whatever that means. Optimal means different things depending on what your goals are. If your goal is to make one user very happy, you might have a different approach than if you have a goal of making multiple users all fairly happy. Kind of make sense? So our punchline here is that things aren't so cut and dry with computing. Fast isn't always fast. Similarly, optimal isn't always optimal. What's optimal in one circumstance might not really be optimal in another circumstance. So that's why we have, when we look at software things, we have server class operating systems and we have consumer operating systems. So Windows 10 is a personal operating system. Windows 10 Server is a server operating system. Even though at the core of both of those, we have effectively the latest, greatest Windows NT kernel, the tuning, the settings for each of those operating systems is different because the assumption is being made that the server operating system is going to be used for in a application where multiple people are going to be making requests of that machine at the same time. Whereas Windows 10 Consumer is assuming you have a single user. We have one person we need to impress. So all the decisions that operating system defaults to is all about making that one user think that the center of the world revolves around them. Make sense? Okay, so this idea of faster or slower, when we deal with technology, the answer is almost always it depends. But then that means we need to give some explanation, right? So, correct answer for which is faster, SCSI or IDE, is it depends. We've already said that SCSI is going to be for multiple users using the thing at the same time. IDE is for single users. SCSI is also a serial technology. IDE is a parallel technology. Something we might also throw in here is, so we'll kind of come back with it. We kind of already said fast means different things or something like that. Let's go here. Parallel in general is considered to be bursty. Serial in general is considered to be steady. So now you might have a situation with a parallel technology where you might have a pretty big range between your fastest speed and your slowest speed. The average might be somewhere in the middle, right? As it always would be, I suppose. But you know, the range is kind of all over the place with parallel, because by nature, because we're sending things in bursts, it's going to be bursty. The nature of the data, the stress that the requests are putting on the other I/O devices, because even though your hard drive is a single device in and of itself, it's still vying for resources with the motherboard. Because whether it's data coming from RAM or from the hard drive or from the GPU or one of these I/O devices, they're all flowing through the motherboard. And if you have enough stuff going on at the same time, this guy is going to, you have a traffic jam. It's a highway. Too many cars on the highway, things slow down. All right, so we're not necessarily guaranteed that we have zero slowdown here if you have a lot of other things going on. All right, but even if we assume that nothing else is getting in the way of our hard drive, this hard drive is still intermittently receiving information because the nature of our data is not necessarily consistent. You might not have data that's always evenly divisible by 8 bits, right? You might have to send a burst that only has 1 bit in it. Now you have 7 wasted bits. How do you process 7 wasted bits? You got to figure out that, oh, this is the end. Now I got to reconstitute this. That kind of tells me we're done. Depending on the nature of data, if you send a whole bunch of zeros in a row, that could be potentially compressed data. Now we have to decompress it. So, the punchline is that because data can be variable, sending it in bursts and then having to put those bursts back together means that algorithm on the endpoint, where we're actually having to reconstitute it, has to take a lot of things into consideration. How do I rebuild this? Do I ignore those 7 bits that aren't there, or are they actually zeros? Kind of make sense? Lots of things going on with that. Serial, just nice steady pace. So you probably have a situation with, let's call it equivalent lineage serial versus parallel technology. So for instance, SCSI and IDE, where they are out at the same time, where you have the average speed of both of them being similar to each other. It's kind of a little bit hard to say because technically there was like 30 different SCSI technologies, but let's just roughly say they were similar to each other. But the maximum speed of parallel for a while was faster than the maximum speed of, let's call it the average SCSI. But the slowest speed of parallel was slower than the average SCSI. So now what you have is would I rather have something that's kind of all over the place like this, or I rather have an equal footing? If you're only trying to make one user happy, and you're not trying to share the wealth between multiple people, and you can get maximum speed from parallel, doesn't it make sense to use a parallel technology for a consumer when you're trying to make one user happy? If the maximum speed of that parallel is faster than the maximum speed of the SCSI, even if the average is kind of all over the place. Because just like, so we might say the job of a computer is to fake out the end user. So if I'm the operating system and the hardware and all this stuff, and we're the person sitting in front of it, it doesn't matter what the box says in terms of what our speed of our processor is, or what the speed of our hard drive is, or any of that stuff. That doesn't mean anything except for ego, right? At the end of the day, if we feel that it's fast, it's fast. Okay, so that's a 13-inch MacBook Pro? This guy? Okay, so we have in our department a 12-core Mac Pro with, I think it has 32 gigs of RAM and a couple, I think the processors are maybe 3.8 gigahertz Xeons or something like that. Pretty powerful machine. Which machine is faster, that or that? Okay. The answer is it depends, right? All right, so do you think if I sat down on your computer to check my email or sat down at the Mac Pro to check my email, do you think I would perceive a difference?
Yes.
What, the laptop might be faster?
No, the Mac Pro
Has the giant screen? In terms of speed, do you think I would perceive a real difference?
Ethernet connection.
Oh, well, so you open up that can of worms. So is an Ethernet connection faster than a Wi-Fi connection?
Generally, yes.
Okay.
If the base
Defend.
connection is the, if the base connection is the same, the Ethernet would be faster than Wi-Fi.
Perceivably?
No, unless there's lots of background traffic.
Okay. So, well, then you also have what are you trying to use the network for? Are you sending a file locally from one machine to another on the local area network? Or are you trying to download a file from Amazon or from Apple or Google or something like that? So now you have a network that might be capable of a gigabit per second, local area network. You have a source for the file that maybe can upload it to you at, we'll be kind and say 3 megabytes per second. So your download speed is a fraction of what your capable transfer speed is in the network. So it might be indistinguishable between the two for speed. So there's a difference between capability and then realized speed. So kind of all these things are like all over the place. We always have this perception of our end user, and the job of a computer is to always fake us out. What percent of I'm just going to ask you to just make a guess on this, but what percent of internet consumers do you think know what speed their internet connection is? I think I usually ask this in most of my classes. Do all of you? Do you know what speed internet you have at your place in Port Washington?
I know what it should be.
Oh, okay, what are you paying for? Let's go that route.
3.5.
3.5 what?
Megabytes per second.
You're paying for nobody sells 3.5 megabytes per second.
Megabits per second. 3.5.
Nobody would sell it as 3.5. So let's do 3.5 times 8. Is it 28 megabits? What are you paying for?
It's like the lowest of the.
You might actually have 3.5.
Nobody sells 3.5 megabits.
Yeah,
Who do you go through?
it's Time Warner, and like everybody's constantly telling us to upgrade, but
Time Warner's budget pleaser has to be 10 megabits. Nobody sells 3.5 because it's on an Ethernet. All right, so you're claiming you should be 3.5 megabytes or megabits?
3.5 megabits. I think they have it.
yeah,
Let's look at the packages.
and it's tested at like 1.2 before.
Are you looking at upload speed?
No, I'm
Sure,
down-
because their
yes.
standard is 15.
Yes. I'm serious.
Maybe your place just sucks.
Well, no. So hold on, but so now we're just lies are amiss. So when I ask the question, it goes like, "Well, I know what I should be getting." It sounds like maybe you don't.
No. We don't get what we should be getting. And what we should be getting is still.
So
very
are you
low.
getting 3.5 then?
Well, then we have 3.5 what?
Where is the 3.5 coming from?
That's what they say we should be getting. So, but if other people in the neighborhood,
That's half of a 6-inch sub if you eyeball it. This is subway math.
It's shared between the entire neighborhood. So like when other people are
Yeah,
like,
that's a cable modem technology is a shared technology, but nobody sells 3.5 megabits. So the if it's Time Warner, you're saying their base package is 15 megabit. So 15 megabits should get you 15 divided by 8, 1.875 megabytes per second. Okay, and we're going to talk about that number conversion stuff because kind of the point of this is more of a consumer awareness type thing. Most consumers don't know what the difference is between a megabyte and a megabit. And probably only half of us in this room know what the difference is, and it's probably because I've harped on it in so many of the classes these guys have had. Then you have the misleading commercials that just say, oh, it's 20 meg internet. It's like, oh, it's like, okay, so the idea is that all these places are selling internet in terms of a speed in bits, lowercase b, instead of bytes, which is a package of 8 bits. So the slowest your advertised speed should be is 15 megabits. I can see like companies like Time Warner and Comcast, they do have like some like my sister-in-law is on one of these like low income plans that offers a lower rate for like really cheap. I think she pays maybe $10 a month or something like that, and you have to qualify for it. I want to say she gets 10, or maybe it's 8, something like that. But nobody sells 3.5. That's just a made up number. Yeah, but nobody would sell it as 3.5 megabytes. They always do it as megabits. So if it's 3.5 megabytes, then it would be 28 megabit, which likely means that it's the 30 megabit plan that you're on. But whatever. So the point is so yeah, the question that we're kind of focusing on here is, and we've kind of proven it here, that the average consumer doesn't necessarily know what they should be getting at home. Right? We have what we have. We don't know what we're supposed to be getting, but we have something. Now, does somebody who has, so like I have 100 megabits at my house, okay, and he has 3.5 made up units at his house. All right, so now with those two things in mind, is my internet faster than his? It's true. Depends what we're using it for. We're both checking our email, as long as like his internet's on, it's working. Okay. If we're checking email, is there going to be a perceivable difference between, my 100 megabits per second and your whatever made up Smurf email or internet?
With that much of a difference, probably.
Probably not. It's going to be imperceptible. All right. So what do you have at your house? You have 50?
Yeah.
Okay.
I actually get 60.
Oh, fine. Yeah. So you have is yours Time Warner, right? So you have Time Warner's highest plan. That's their premium. Yeah. So I'm on Time Warner's highest plan as well, but I was one of their beta testers, and they never turned me down. So they have they used to have up to 200.
You had grandfather.
That's it. Yeah. So but they never changed the thing on my account. So the bandwidth is there. They just are throttling it at like 50 megabits, and then they under promise, over deliver. So that's why you're getting 60. And he's paying for like Rice Krispies and 2-week-old milk delivery. that's his internet. What's this?
He has no idea what he's getting into.
Oh.
Here's one of your homework assignments. Go home and run a speed test, please.
I did, and the upload was faster than the download.
Yeah.
we used to have that here on campus.
Yeah. Well, no, I mean, I believe you.
Yeah.
Just I'm interested in what you actually have. I think they were really referring to that you don't know what you're getting into with me.
Yeah.
That's true.
I'm a little bit different kind of teacher than you might have at some other places.
We tried to get a student to have like frequent nosebleeds in class my first semester.
That was entertaining. That was nosebleed.
I forget what his real name was because he didn't take any more classes.
He would sit right in front too. He was like right in front of me, and I don't know, this guy must have like a deviated septum or something. I mean, this dude would just have just huge, just flowing nosebleeds in class. It was awesome. Yeah, I just love that.
It's almost as good as Amish.
Oh yeah, I miss Amish.
Yeah. Where did he go? Oh, he works for the
He graduated.
insurance company.
Yeah.
In, Sheboygan.
He's a cutie.
Has all the money.
All right, so
In the ferry
kind of
office.
let's refocus. All right. So speed means different things. So if you say you have 60 megabits at your house, I have 100 at my house, it's going to be imperceptible, right? Majority of very, very few times are we going to ever maximize our internet connection. We talked about it in our class earlier today. Maybe the only time would be if you're doing like BitTorrent or something like that, where you're downloading from multiple sources at the same time, and each source is giving you, let's say 200 kilobytes a second, but all of it adds up to whatever the maximum size of your maximum bandwidth that you have is. So possibly doing like a BitTorrent or something like that, you could maximize your internet connection. And maybe, we're on the slower side of the theoretical maximum. Like AT&T is about to put gigabit in downtown Milwaukee sometime relatively soon. So we're obviously significantly slower than that. So it's probably possible that a place like Apple or Google could feed us data at 100 megabits per second or 60 megabits per second if the moon's aligned. But a majority of the sources for our data, if we're downloading something off the internet, their upload speed is our download speed. All right, so if I'm downloading something at my house, I'm reliant. I can only download at the maximum speed. Well, I can only download at the lesser of my maximum download speed and their upload speed. So chances are my download speed is going to be higher than their upload speed, more than likely. So the fastest I can download is whatever their upload is. And most places are not going to have upload like Apple and Google. Most places are going to have reasonable upload, where maybe you can download stuff at 2 megabytes per second. So 16 megabits per second, something like that. So the whole real reason why we have these giant bandwidths is if you have multiple things happening in your house at once. You're watching Netflix in one room, you're downloading from BitTorrent in another, you're also playing an online game. You have all these different things going on that all are downloading stuff from different sources, and they all add up to some number that's greater than some minimum that you need to make sure you're paying for enough bandwidth to get that.
Well, let's be realistic. You're doing Netflix and chill while BitTorrenting the same movie over here. And
To watch later.
right.
Yeah, something. I just learned that phrase last semester. My students taught it to me. Netflix and chill, apparently. It's a thing. Yeah, it's something they don't teach that at Sandwich Art at school.
University.
He's got the sticker setting.
It's not as good as anymore. Not as accredited anymore. Your spokesperson got arrested.
Oh, that's true. Yeah, nobody talks about him anymore.
Don't say his name.
All right, so in any case, speed is deceptive, right? And we can't just say that something is faster. And an overall goal for us, whenever we're talking about anything in technology, is ultimately to fake out the end user. Okay? If the end user doesn't know any better, it doesn't matter what the actual speed is, as long as they think that everything is happening fine, right? So if you were paying for 20 megabits per second and actually getting 4 megabits per second, but you were happy with what you were getting, you would be none the wiser, right? Most consumers don't even know how to check what their speed is, right? So that's kind of our idea here. So when we're dealing with a parallel versus serial type of technology, parallel being bursty, an end user isn't going to be able to, at the granular level, deal with those ebbs and flows. They won't be able to perceive that. From their perspective, it's going to kind of give you this download speed, if you will, of how long a file is taking to copy from this place to this place on your computer. And that's kind of your hard drive speed. And that's going to show you kind of an average rate, because you're not going to see the crazy little spikes in there. And then from their perspective, it's going to feel like, oh, this is pretty fast. Where if you were on a SCSI connection, presumably sharing that hard drive with multiple people. And again, we're back to this idea that a hard drive can only read or write one thing at a time. Okay, it's the nature of the hard drive. It's probably going to change now that we're moving towards solid state and looking at ways of kind of evolving the idea of solid state drives. Solid state doesn't have any moving parts, so there isn't necessarily a reason why we can only read and write things at one time, other than the fact that that's what all drivers have been written for at this point. So operating systems have been written to talk through a serial ATA interface to a hard drive, whatever the technology of that hard drive is, to tell it to read and write one thing at a time. Technically, a solid state drive could do more than one thing at a time. There's no moving parts. But now we need to make sure that, you know, if you write to two places at once, you need to make sure that those guys don't conflict with each other or doesn't break something else. And so there's overhead that comes into it. We're going to talk about some of that stuff when we talk about parallel processing and things like that as well. So in any case, it's ultimately about faking out the end user. And when we're dealing with SCSI, and we have, let's just use in our example, 3 end users. So if we have 3 end users and they're all sharing a single hard drive that can only read and write one thing at a time, the chances of one of those end users experiencing one of the slow points of a bursty connection or bursty speed interface is higher, because now you're dividing it by 3 people, right? If we have 3 people all looking for the speed, there's a higher % chance that one of them might get the slow speed. Where when a single person is using a parallel connection, they're guaranteed to get the slow and the fast speed. And since they're not competing with anybody, it's not going to be perceptible to them. Where if you have 3 people who aren't necessarily sitting next to each other, so they're not going to have this idea that, oh, this guy's going really fast, I'm going really slow. They're just going to have this idea that, oh, this seems like it's taking longer than it should be taking. It's not going to feel fast to them. So they're not getting to participate in that bursty, the bursty highs. Now, when we deal with a server type thing where we have multiple people, we're often playing to the worst case scenario. If we can give a baseline for a worst case scenario and say, this is what it's going to be on average for everybody. Not sometimes it's fast for some people and sometimes it's slow for some people, but it's going to be, give this on average for everybody. Then we can have a situation where the users who are using the system are going to get consistent performance and will likely adapt their expectations based on the performance they've gotten on that machine. That makes sense? So regardless of what kind of computer you have, if you use your computer very often and one day it's running slower, you can perceive that, right? But maybe your computer running slower is running on turbo for somebody who has a 5-year-old laptop. And they look at you like, how could you say this is slow? And from your perspective, it's like unusable. Like, I don't even know why I opened the lid. This isn't a computer. It's a paperweight. This is a paperweight. All right, so perception and kind of goes all over the place, I suppose. All right, so let me go back here. So this is SCSI IDE. So these are kind of at war with each other. And out of this war, who won? So we're looking at kind of the late 90s. So serial versus parallel. Who came out of that fight? Do you think serial won or did parallel win? That got us to where we are today. Where today we're on serial ATA, which is serial. One of these two technologies went away. One of these two went away for our hard drives. You think SCSI won? Yeah. Nope, SCSI lost.
Okay. You said that for a while there was SCSI, but mainly it was IDE. That was the only one that was before.
Yeah. So technology tends to go in these ebbs and flows. So for a while, IDE was substantially faster. So our parallel technology for interfacing with hard drives was substantially faster than our serial technology for interfacing with hard drives. SCSI kind of stopped getting faster and IDE just kept going. So it got to the point that even though it was bursty, we were sitting in a situation where its slowest speed is twice as fast as SCSI's fastest speed. So it doesn't matter whether it's bursty or not, it's just faster. It's just plain faster. So So SCSI lost that war, IDE took over, and actually IDE was the technology that we used until serial ATA came out, which is 1.5 gigabits per second when it first released. So we had a big jump. So that was a major move. So IDE didn't really have a competitor. Just all of a sudden you had a brand new interface, which was the serial ATA, which kind of took over. There was a couple year period where they were in competition, but then there really wasn't.
So what made them go back and try a serial way to do it again?
Okay, so interesting question.
Because if the serial architecture died out.
All right, so we've kind of already answered that earlier tonight, but let me ask it a different way. Why do you think SCSI failed? Is it because serial was the wrong choice? Or was it because the technology we had at the time for serially loading bits onto a wire and serially removing bits from a wire wasn't keeping up with the way we could do it then in parallel? So it has less to do with SCSI as a technology and more to do with the technology of those days being able to take advantage of a serial type technology efficiently. Earlier tonight I kind of talked about this idea of how long does it take to put one bit onto a wire, send it, and download one bit on the wire, as opposed to putting 8 bits on a wire, sending it, downloading 8 bits off the wire. Is it 8 times slower? I think I probably asked the question kind of like that. It depends. Back then, once IDE got sufficiently fast, we got to the point where we can send things 8 bits at a time. Let's just keep using that number. Fast enough that under very, very few circumstances was serial better back then. But at some point in time, as our technology gets better for maximum speed across a new kind of cable, the serial ATA cable, as well as whatever technology we had at the endpoints, the interfaces, getting bits onto the serial cable, getting bits off of the serial cable. Because now we have a cable that can go, I think today's serial ATA is 6 gigabits per second, but 1.5 was kind of day one serial ATA. So even though you can do 1.5 gigabits per second back then, nobody was putting bits through there at 1.5 gigabits per second. So that was tons of bandwidth that we weren't taking advantage of. All right, but we had a technology that could get more bits onto that serial ATA per second than our technology at the time from parallel getting it onto an IDE cable. So it was beating it because our interface technology improved. So we got better at dealing with serial, better at marshaling bits onto that interface than we were back in the SCSI days. Kind of makes some sense? So this kind of goes back to this idea of what does fast mean and why did a certain technology lose? It wasn't so much that SCSI was in and of itself the loser. It was SCSI paired up with the two endpoints couldn't keep up with IDE with its endpoints. We were better at sending things in bursts than we were at sending things 1 bit at a time then. You can make an argument that we might still be better at sending things in bursts than we can at 1 bit at a time today. But if serial ATA has a significantly faster max speed than, nobody does anything in parallel anymore for hard drives. Well, at least not internal hard drives. So with that in mind, did parallel die? So we would have said back here that maybe serial died. Well, really, we're talking about hard drives, right, in this world right here. So when SCSI died, were we using serial to connect anything else to our computer? Any other I/O devices that maybe were still using serial? I love these conversations with people who should know the answer. Printer?
Most other things.
All right, so old Alex said printer. So given that you said printer, why don't we go ahead and start this slide for parallel technologies? All right, so parallel, we had printers. In fact, printers back then used a cable called a Parallel cable. All right, we've probably seen those before. Let's look it up. Parallel cable. Look at that guy. There's your parallel printer cable. You got one of those at home, old Alex? No. Okay, so that's a parallel cable. So printers would have used that guy. What used serial cables? Here, I'll leave in just to show you they existed. We'll do serial cable so you can see it. So here's a serial cable. No, looks like a monitor. Monitors would be called a VGA cable, but they do look similar. So back in the late 90s, let's say, or even we can go before that. Let's say mid 90s, mid to late 90s. What did we use serial cables for? All right, so pause that for a second. When is serial better? Up to this point, we've only really discussed speed, right? Kind of human nature is, well, faster is better, right? It's not necessarily always the case, but that tends to be our go-to move. Well, whichever one's faster must be better. So if I've told you in the late 90s, IDE was faster, which is why SCSI went away for hard drive technology. So from that perspective, generally speaking at least, because actually there was a serial technology still used for a while before serial ATA came out called fiber channel cables. That was a serial technology and really expensive. So that was kind of the replacement for SCSI if you had unlimited dollars and you were running servers. But generally speaking, IDE won that battle. So we decided that speed was the most important measurement for hard drive connectivity. So with that in mind, since serial obviously didn't die off, serial cables still existed. We don't see them like that anymore. Our serial cables today look a little different, and we're getting to that punchline here in a few minutes. But when serial, so punchline is serial did still exist. When would serial be better, and why? We want to kind of put our computer science minds together and think about the nature of sending things one bit at a time versus in bursts at a time. And when does sending things at one bit at a time possibly benefit us? Well, earlier we mentioned that the speed of a connection for when we were trying to decide if parallel or serial was faster, we decided that, well, with serial, you don't have to worry about doing anything special to get the bit onto the wire. You don't have to worry about doing anything special to get the bit off the wire because everything arrives in order, right? So there's not you're not fussing over the data. We're not touching the data. We're just sending it and it's arriving and we're retrieving it. We don't have to reconstitute it or anything like that. The fact that we've decided that, you know what, we can actually do parallel faster doesn't answer necessarily when serial might still be better. I'll give you want a hint? I'll give you a hint. We use serial cables for modems. What's a modem? So we're back to internet stuff. All right, so modem stands for modulator demodulator. Even though today your DSL, they call them DSL modems, they also call them cable modems for your cable internet, even though it's not modulating and demodulating anymore. It's just more of a historical thing. But back then, we needed a modem because how was the internet delivered back in the 90s? telephone, dial-up, telephone lines. Okay, so we were using a digital device, a computer. Let's see, now we're starting to get to organization and interface stuff. I'll just delete these. So there's our PC. What color is digital? Here are your choices. Orange? Digital orange? Great audience participation here. Way to go, old Alex. No, I already chose orange. All right, we went blue for analog? Okay, so this is our telco. That's our telephone line, right? Here, we'll make it skinnier like it's a line. All right, and this is analog. Okay, what's the difference between digital and analog? Besides words.
Analog's on off.
Okay, close but completely opposite.
Or is it digital's on off and then analog's sort of wavy?
Okay, so analog looks like a wave, and digital is on off. Okay, that's what it looks like. What does that mean? Why does analog look like a wave? Is it electricity?
Well, I mean, like, that's the wavelengths of electricity.
Well, I guess let's just go with no. That probably takes us down a bad conversation path that's just going to lead to ridicule. So let's deal with it in kind of a practical sense for us. How many of you have a DirecTV or Dish Network, or have ever used DirecTV or Dish Network? Okay. What happens when there's a storm? There's rain. It goes out, right? Now, how many of you have ever watched TV using like rabbit ears? For like all right. What happens when the signal's not so good? Gets fuzzy. Not gone. Gets fuzzy, right? A digital signal is on or off. Okay? You either have a perfect picture or you don't have a picture. All right? So if we can't take all those ones and zeros and reconstitute an image, it just says signal lost on digital, right? With an analog signal, like you get from your rabbit ears or an antenna, there's a whole big range between perfect and non-existent, right? You have all sorts of stuff in the middle that might be watchable if you're desperate enough, type things, right? Okay, that's our waveform for analog. So analog is not on or off. You have all sorts of if this is on and this is off, there are points here in analog between those two. With digital, there's not. Digital is here, then there's a drop off right to off. Okay? Digital works great for computers because we need that discrete decision making, right? That's why we use binary. We're going to be dealing with a lot of binary stuff in here. Binary and hexadecimal out the wazoo. It's going to be amazing, all right? But computers need that discrete logic in order for us to actually write programs that have decision making involved. Humans are analog beings, right? There's a such thing as us sort of hearing what somebody said or sort of seeing a sign. With the computer, it's either we saw it or we didn't. We heard it or we didn't. Make sense? So we have two different things. This telephone line here is an analog line. So things are sent across this in a wave format. Okay? There's interference. There's fuzziness. There's a good quality signal all the way up to a low quality signal, and all of that might be usable to some level. If you're talking to somebody on an analog telephone, it might get fuzzy, but you can probably still make them out until it gets horrible, right? All right, so we're going to have this, as old Alex suggested, in blue. Blue is our analog. All right, you're good with that? Or you want a different color? You got to speak now. Blue's fine? Okay. So this is analog. We have our PC, which is receiving our internet. Okay, so the internet travels across this telephone line. And over here, without getting into too much detail over here, there's the internet. Okay, so the internet's probably a little bit more complex than this little box that we just drew, but that's the internet. All right, internet lives over there. Well, I mean, if you wanna go back to back in those days, this would probably be a BBS, a bulletin board system. So something like Prodigy was one of the early ones. So this guy would be a server at some place probably in town that had a bank of a whole bunch of modems. All right, and when you dialed in from your house to this place, you dialed into one of those modems. All right, and how many of you have ever done dial-up before? All right, so when you do dial-up, what happens?
I don't know, repressed memories.
Oh, we got okay. So let's the impression of dial-up. Go ahead. That's it. That's not going to be a solid connection because there's usually some beeping. It's like.
Yeah.
He's been listening to dubstep.
All right, so now, so what's that called? When all that beeping and stuff is going on, what's actually happening?
That's the waveform.
So that's the wave.
Conversion?
Oh, okay. Conversion of no. None of you have had a networking class? Get your computer science degrees.
Question.
All right, so all that beeping and stuff like that is something called handshaking. All right, so handshaking is our beeping. All right, and we have to have gotta put our modems in here. So here, these are going to be our modems. Modems are going to be green here. Is that okay with you, old Alex? There we go. All right, so those are our modems. So when we connect with our PC using our modem across this telephone line to our bulletin board system to one of their modems, and we hear all that beeping, we're having handshaking. The beeping is handshaking. It's a synonym. What are we actually doing during that handshaking? Well, they would be. Yeah, they are communicating, but let's take it a little deeper than that. So far so good.
So is it taking what's being sent over the analog and converting to digital?
Isn't that kind of like saying, are they communicating?
Yes. So, but then my conversion answer before was somewhat correct.
Well, no, you haven't given me the right answer yet.
So communicating.
Well, yeah, I said communicating is a starting point, but I said let's go deeper. So yes, they're communicating, but it sounds like there's a fight going on, and I'm calling it handshaking. So they're shaking hands. Probably we named it that for a reason. What are they trying to accomplish?
The internet, the information that the PC is requesting is, the BBS sends the information to the right PC. The information is.
Okay, so now all of you have said you've done dial-up before, right? When all that beeping and stuff is happening, has any information been requested yet, or is that during the initial connection? You're waiting for the magical connected thing to pop up, right? Before you go to the Google.
So it's just establishing like a dedicated connection to
Okay.
external.
Now we're starting to go in a decent direction. What does it mean to be a dedicated connection? So we're communicating. We're attempting to establish a dedicated connection. All those are good words, great words, Trump words. Those
The
are
best words.
those are the best words. Okay? So we're establishing a dedicated connection, but what does it mean to establish a dedicated connection? Also true. Yeah. So I mean, you're gonna have to log in to make sure you're allowed to connect. Fine, but actually, even before that happens, though, because at that point, that's when information is actually being sent. Yeah. So that's when you're sending username and password to the server, and they're trying to corroborate that you are who you say you are. But the handshaking occurs before that, and the job of the handshaking is to establish a dedicated connection. So what I'm trying to get you to think through is, what does it mean to establish a dedicated connection over an analog medium between two digital computers using modems in 1998? So pause this for a second. All of us in here, with the exception of old Alex, are speaking English. For the record, I've known Alex for a very long time. so this isn't like first day, I'm just being a jerk to him.
No,
All right.
be honest, you do that to a new student too.
Probably. It's probably true. Yeah, I did say he was an 8, didn't know what his internet connection was. That's pretty bad, dude.
I mean, he's better than Amish. Like, he has an internet connection.
And one of our undergrads, he just graduated his last year. He, for 4 years, had the nickname Amish.
Still has it.
Because nobody even knew what his real name was. Day one of class, I tend to give nicknames. But day one of class, when he was a freshman, I made some reference about some TV show or something like that. He says that, was the Super Bowl? He's like, oh yeah, I don't really watch TV. So I figured, oh, you don't watch TV, no electricity, must mean you're Amish. Stuck. 4 years.
We had a quiz third year of what's Amish's real name, and
People failed it.
15% of people couldn't get it.
These were people that knew him for 3 years, did not know what his actual name was.
15% of the people could get it.
Yeah, they didn't know what his name
What
was.
his name?
Yeah, that was awesome.
If that's not like worth it that long, I'd say that's a success.
One of my talents is creating these backstories that stick. I mean, take the Mr. Gonzalez. Yeah, that's maybe.
Yeah, the one that your wife
We don't want to overload
pays you
him with
for.
some of that stuff. That's probably a future class discussion for you to get introduced to Mr. Gonzalez and cousin Lupe and Aunt Jemima, Caesar. Now we're just let that marinate.
Farm,
We're just gonna let that marinate. All right, so let's get back to this because we're just adding on to our next break time here since we're getting off topic. All right, so what is necessary to establish that dedicated connection? So we're going to take this to real life stuff. So we're all speaking English in here, right? Okay, even old Alex, we're all speaking English. Now, if we're far distant from each other, we can see each other, but we're far away, so we couldn't hear each other. Okay. So maybe we have binoculars or something like that we're looking through so we can actually see each other. So we've decided that we're going to communicate through hand gestures. Okay? So we need to be able to establish a protocol, establish a communication, a dedicated channel. So me and Tim here, this Tim, we're going to establish a communication protocol. Now we've decided that we're using hand gestures, which means that we must be able to see each other, right? And we must be able to see each other at all times that we're trying to communicate with each other using those hand gestures. Which means that if I'm going to be looking here and then looking away, you can't be giving hand gestures while I'm looking away. Otherwise, I'm going to miss the message. Make sense? So we have to establish a cadence for which that we can successfully communicate with each other. All right? So the same thing is kind of happening here. All that handshaking, all that beeping, what they're doing is they are deciding what is the fastest speed that they can communicate with each other without having errors, without missing hand gestures. Okay, what is the fastest speed that this modem can send and receive data with this modem over this analog connection such that no errors occur? Why was it important that no errors occur in 1998? Really, probably 1996 is the better question, because we're dealing with those transition years there. So let's keep it at 1996. Why was it important that no errors occurred? That they didn't try to go too fast? Because back then, you might have a 90s, you'd have a 56K modem, and sometimes you'd only connect at 26,400 bits per second. Because that was the fastest they could negotiate over the current quality telephone line, such that there were no errors. So even though both sides were capable of 56K, there was enough noise over the analog channel that they decided at 56K we have problems. This is the fastest that we've been able to handshake and decide that we can send information and always be able to understand it on these two sides. Why could there be no errors in 1996?
Is it because it was going over the analog, so there was no way to, no way to tell if you had an error?
Okay.
You
You're
received
actually
it,
closer to right than you should be, or I think that you know you are.
Like, there was no way to track whether or not an error had occurred.
Okay.
A long way.
Even closer, but I still don't think you knew what you said. Okay, so let me. How many of you have heard of that before? TCP/IP. All right, what is it? Okay. Well, protocols so far so good. Specifically, what is TCP/IP? What's that protocol for? We have all sorts of different protocols, right? For do different things. TCP/IP is one of many, 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 many protocols that we use.
Endpoint identifications.
Ebo's deciding what the Google says about this. Were you a double major in CS and math?
No, it was just math.
Oh, see, he has an excuse. So these two have excuses.
Took most of the classes though. Didn't count.
Okay, so these two have excuses. You have no excuse. You should know what TCP/IP is.
Endpoint identifications.
But you're just like making up words. What is it? I don't care what it stands for.
It's an address.
What's the protocol for? What problem is it solving? Just like English is a protocol. So when we speak English, we're solving the problem of successfully communicating between human beings. What problem is the TCP protocol solving? Keep in mind that I've been really harping on this idea of in 1996, it was super important that we didn't have errors. Clearly, we've heard about TCP/IP more recently than that. It's kind of a term that we know exists today, right? Might it have something to do with that whole problem of we can't have errors in 1996? So TCP/IP deals with data being transported over a medium in such a way that we validate the successful transfer of the data and resend if necessary. All right, so it allows for errors and recovers from them. That's the point of TCP/IP. All right, so without TCP/IP, we have to drop down to the lowest comfortable speed we can go at without falling off the bike, okay, without having errors. With TCP/IP, we can push the envelope expecting that most of the time we're not going to have errors. But if we do, we can recover from them. And TCP/IP manages that for us so that we're none the wiser. It's kind of magically happening as part of that whole communication protocol. So now, when we send stuff over the internet, we're not just sending it one bit at a time. So TCP/IP specifically works on what's called packet-switched networks. So we load bits into like a packet, and then throw that packet onto the network, kind of like parallel technology. But that packet has some other information associated with it. You've heard of things called packet sniffers before? Okay, so they're listening to what are called datagrams. So they're listening to stuff on the network, and then you can piece them apart, and they're inside that is your payload, your actual data that you're trying to send, as well as some other information that allows you to reconstitute your data on the other end, as well as make a request back to the original sender in the event that data was corrupt or missing or something like that. All right, so back in 1996, when we were doing this whole dial-up modem stuff, we didn't have TCP/IP governing this connection. So we didn't have a backup plan. We didn't have that guy that says, okay, well, you know, if we mess up, we'll just go as fast as we possibly can. If we mess up, we'll just recover. We had to go as slow as we can confidently send data so that we didn't have screw-ups. That make sense? That's what all that handshaking is about. All the beeping and all that stuff is all about not having errors. All right, so let's see here. So that's HD, parallel versus serial there. Parallel versus serial in terms of IDE. So to answer this question, when is serial better? Spelled variance, is that right? Nailed it. All right, so serial is better when we need to limit errors, in our example we just went through, or variance. All right, so we're going to talk about an example of variance next. When did we start this lesson? Well, actually, I can tell you. Yeah, we've been going for an hour. All right, so we have to take another 10 minutes because you guys are checking out, right? How many of you are? Out of curiosity, how many of you are checking out?
I really got a piece, so.
Well, then why don't we talk about variance first? I'm more interested. Like, would you say this is about like the time when things start like? Really? So there's some like truth to this whole thing?
When they kind of also depends on how much interaction there is in the class.
Oh,
Like,
so
if we sit here and we don't say anything for like an hour,
Yeah, I'd
probably be done.
Right.
There was more conversation in the session than the last one, so we probably are less.
all right, so to take 10 minutes. So 8:35.